we have only two-player games, so we will have only two players. We have to define the legal or the possible moves for each player, and we have to determine the outcome or the reward of the game. So here, since we are considering only two-player games, we will call the first player the max player, and the second player, we will call it the min player. Later, we will see why we give them these names. So the first player, either the max player or the min player, will make the first move, and they will take turns till we reach a terminal state, which is the game over situation. So the first step, we have to define what is a state in a game. So state is what is the configuration of the board. So if we take the chess game, in the chess game, the state is the configuration of the board, which is the position or the locations of the white pieces and the black pieces. The initial state is what, denoted as S0, will be what will be the configuration of the board before doing any move. So if we take the example of the chess game, the initial state will be the configuration of the board or the position of the pieces before doing any move by the players. The second component is the successor function. So the successor function in a single agent problem, the successor function has as a parameter only the state. Here in the successor function, we have to define two parameters. We have the state and the player, because the children of each state are related to this player. And the successor function will return what? Will return a set of pairs, action and successor. The third component is the terminal test. So the terminal test in a game is the game over situation. So it's either a win for one of the two players, which means a loss for the opponent player, or it's a tie or a draw situation. There is no winner. The last component in problem formulation is the utility function. So what we call utility function or the objective function or the payoff. So what is a utility function? Is an estimation of the value of a terminal state. So for each terminal state, either it's a win or a loss or a draw situation, we have to give it a value. So we give this value according to what? According to the max player perspective. What does it mean? We will give a high utility value if the state is a win for the max value, for the max player, sorry. And we will give a state a lower utility value if it's a state which is a loss for the max player. So if we take the example of the chess game, in the chess game, in tournament, they use +1 for a win, 0 for a loss, and half a point for a tie or a draw situation. So if the max player is playing with the white pieces and the black king is under attack, so it's a winning situation for the max player, so we will give this terminal state +1. If it's the opposite, the white king is under attack, so it's a loss or a failure situation for the max player, we will give this terminal state a 0 point. If it's a draw, it will be half a point for each one of them. So a game tree will be what? Will be of the game tree. It will be the same as a search tree. So the nodes will be what? Will be the set of the game states, and the edges will be the moves applied by different players, either the min player or the max player. So the game tree starts with the initial state and the branches out to show the possible successor state resulting from player moves. Now we will take the example of the tic-tac-toe game. So it's the cross knot. So it is the cross and knot game. So one player will play with the cross and the other player will play with the knot. First, we have to define a state. What is a state in this game? So a state is the configuration of the board. So it's a grid, a 3x3 grid, which represent a state. Then we will define the initial state. So the initial state in this game will be what? Will be an empty grid or an empty board before any of the players is making a move. The successor function will be what? Will be the possible moves that can be made by each of the player. If we apply the successor function or the initial state, and the player is the max player, which is playing with the cross, so the successor function will generate a set of state of 9 possible moves, and each one represent putting the cross in one of the empty squares. The terminal test will be what? Will be to check if it's a game over or not. In the tic-tac-toe game over, we have 3 situations. We have the situation when we have a line with 3 crosses, which is a winning game to the player playing with the cross. We have the second terminal state when we have a line of 3 knots. And we have the third terminal state if the board is all occupied and there is no empty square. And no one of them has a line of 3 pieces. So if we want to assign a utility value for each of these terminal state, so it will be, for a winning state, it will be +1. For a loss state, it will be -1. And for a draw, it will be 0. So if we take the max player is playing with the cross and the min player is playing with the knot. So the terminal state, when we have a line of 3 crosses, it's a winning situation for the max player. So we will give it the high value of the utility function, which is +1. If we have a terminal state with a line of 3 knots, so it's a loss situation for the max player, so we will give it a utility value of -1, so the lowest utility value. If it's a draw, which means that the board is completely saturated and we don't have a line of 3 pieces, we will give it a utility value of 0. Is it clear till now?
Yes.
So second step, we have to define to see what is the game tree. So for the game tree, since we have 2 players, we have the max player and the min player. We suppose that the max player is playing with the cross and the min player is playing with the knot. Here we suppose that the player who is building the game tree is the max player. So here we are building the AI agent function for the max player. So obviously the one who will start who is the root node is the max player. So each one of them will take turns, and the max player, since he is playing with the cross, he will put a cross, the symbol cross, in an empty square, and the min player will put a knot in empty square. So here, suppose that the max player is starting the game. For the max player, he will have 9 possible moves. So he can place the symbol cross in 9 possible squares. So how can this player choose the best move between these 9 possible moves? In order to choose the best one, he has to build the whole game tree until reaching the terminal state. So in this, the game tree will be what? Will be a set of layers. So each layer we will call it apply and apply, and each ply is related to a player, either the max player or the min player, since they are taking turns till we reach the terminal states. When we reach the terminal state, we will assign for each terminal state a utility value. Here, if we see the first terminal state, we have a line of 3 nodes. Since the main player is playing with the nuts, so this state is lost for the max player. So we will give it a utility value of -1, the lowest utility value. For the second terminal state, we can see that the board is fully filled, but there is no win. So we will give it, it's a draw situation, so we will give it utility value of 0. For the third terminal state, we have a line of crosses, and the max player is playing with the cross, so it's a winning situation for the max player, and we will give it a utility value of +1. Now, the problem here, how can we use these utility values to estimate the best move in the first stage? So how can we backpropagate these values to the root node and use them to choose what is the best move between the 9 possible moves? To do that, we will use what we call the minimax algorithm. So, in the previous chapter, when for a single agent search problem, the optimal decision or the optimal solution is what? Is the sequence of actions that to reach a goal state. So it's a sequence of actions that leads to a winning terminal state. In adversarial search or games, since we have multiple agents, so the max, if we are building the agent function for the max player, so the AI is helping the max player, this max player has to build a strategy that take into consideration the opponent player moves. So in most of the case, the max player moves are responses to the min player moves. So here, the moves of the main player are crucial to determine the max player strategy. So to do that, we will define what we call, so the optimal strategy will be to use what we call a minimax value function. So this minimax value function will do what? For each node, we will estimate the minimax value for this node, and this minimax value will represent or indicate how favorable the node represented by a state S is for the player P. So the minimax value for a state, it represents how good this node is for this player. So for the terminal node, we know how to estimate the minimax value, since it is the utility value, because the utility value will represent how good this node is for the max player, for a player, either max or min. But for the other nodes, we don't know how. So the only solution is to do what? The maximum player, and we call it max player, since he will look for the nodes that will maximize its reward or its minimax value. And the main player will look for the states or the nodes that will minimize the reward value. So to wrap up, we can use this minimax value equation to formulate this strategy. So the minimax value for a state S with the player P will be equal to what? If this state is a terminal state, so the minimax value will be equal to the utility of this state. Otherwise, we will check if this state is for the player max. So the minimax value of the state S will be the maximum of the minimax values of the successors with the player min. And if the player P is the min player, we will take the minimum values of the minimax value for the successors with the player max. So imagine we have a parent node, and this parent node has a set of moves. In order to choose which move is the best, he has to evaluate, we have to estimate the minimax value of this parent node. In order to estimate the minimax value of this parent node, we have to first estimate the minimax value of the children. And then if the parent node, the player of the parent node is a max player, so we will take the maximum of the minimax values of the successor values. If the player is min, we will take the minimum of the minimax values of the successors. So here we can see that the minimax value function is what? Is a recursive function. So in order to have the minimax value of an ascendant or a node, we have to first estimate the minimax value of the child, and so on. So obviously, we have the utility function of a terminal node. We can use this utility function to estimate the minimax value of their parents, and so on, till we reach the parent or the root node of the game tree. If we want to formulate this equation using an algorithm, first we have this algorithm has two parts. The first part is the minimax function. So the minimax function will have as parameters the state, which is the current state. It can be the initial state of the board, or can be a middle state. And as a second parameter, we will have the player, either max player or min player. So in the minimax function, we will call the minimax value function, which is a recursive function using the state and the player. This minimax value function will return what? Will return a value. Then we will return the action related to this value. So the most important function here is the minimax value function. So we will just transform this equation to an algorithm. So the first step, we will check if the state is a terminal state. If it's the case, we will return the utility of the state. For instance, for the tic-tac-toe game, we will return either +1, 0, or -1. So if the state is a terminal state. If this state is not a terminal state, so it's either the root node or the node in the middle of the game tree, we have to check if the player is the max player. So initially the value will be the most lowest one. So it will be -infinity. Then we will generate the set of successors for this state. And for each successor, we will take the maximum between the current value and the minimax value of the successor by using the opposite player. Because here we know that the player we are using in the parent node is the opponent player that we are using in the children node. So that's why here we have to use the opponent player to call the minimax value for the child node. And we will do the same thing for the min player. So here else, so if the player is the min player, the value initially will be the highest one, so +infinity. Then we will generate the set of successors. For each successor, we will compare its value, which is the minimax value of the successor, using the opponent player, which is here the max player, and the current value, and we will take the minimum value. So the max player will try to maximize its minimax value, and the min player will try to minimize its minimax value. So here we will see an example. So we have this minimax algorithm, this minimax game tree. So here we have 4 layers. We will start with the player with the node A. The node, so the first player is the max player. So here we can see that the max player can perform 2 actions, either A1 or A2. If the max player chooses to play with A1, the min player has 2 options, either playing with B1 or B2. If the max player chooses to play with A2, the min player can choose to play with C1 or C2, and so on, till we reach the terminal states. These are the terminal states. Here the utility values are random. So here I use the random values. But you have to keep in mind that a high value is good or favorable for the max player, and a low value is favorable for the min player. This is always the rule. So we will apply the minimax algorithm on this example. So the first step, we will call the minimax value on the node A. Is this node terminal? No. Is the player max? Yes. So the initial value will be V equal to minus infinity. Then we will do what? We will do the expansion. We will generate the successors. Here we have the successor B and the successor C. So we will generate them one by one. First, we will generate the successor B. When we generate a successor, we have to call the minimax value function on this successor. So we will call the minimax value function on the successor B. Is the successor B a terminal node? No. Is the player max? No. It's min. So the initial value for the node B will be equal to plus infinity. Next, we will generate the successor of the node B, which are D and E. For the first successor, which is D, is it a terminal state? No. Is the player max player? Yes. So the initial value for D is minus infinity. Then we will generate the successors of the node D, and the successors are H and I. For the first successor, which is H, is it a terminal node? Yes. So we will return what? We will return its utility value, which is 5. Then between 5 and minus infinity, since here we are using the max, since the node D is for the max player, so we will take the maximum between the current value, which is minus infinity, and the value returned by the first child, which is 5. So V is equal to 5, since it is the maximum. Then we will generate the second successor, which is I. Is it a terminal node? Yes, it will return the value 12, which is the utility value. Then between the current value, V equal to 5, and the new the value returned by the second successor, which is 12, what is the maximum? Is it 12? So the new value of the node D will be 12. There is no other successors for the node D, so we will just return the minimax value of the node D. For the node B, between plus infinity and 12, what is the minimum value? Since for the node B, we are playing with the min player, so we will take the lowest value. So it's 12. So the new value for the node B will be 12. Then we generate the second successor, which is the node E. E, is it a terminal node? No. So we will give it a value of minus infinity, and we will generate its successors, which are J and K. For the node J, it's a terminal state, so we will return its utility value, which is 11, and we will compare 11 with minus infinity and take the maximum, which is 11. And we will generate the next successor, which is K, and return its utility value, which is 15. And we will take the maximum between 11 and 15, and the value will be 15. There is no more successors for the node E, so we will return its minimax value, which is 15. Between the current value of the node B, which is 12, and the value returned by the node E, which is 15, what is the minimum value? Since we are playing with the min player, it's 12, so we will keep the value of 12. There is no more successors for the node B, so we just have to return or back propagate the value of the node B, which is 12. So the arrows here are what are the back propagation, or when we unfold the recursive function, unfolding the recursion. Next step, for the node A, between minus infinity and 12, what is the maximum? It's 12, so the new value for A will be 12. We will do the expansion of the next node, which is C. We will give it a value of plus infinity. Plus infinity. It's not minus infinity, it's plus infinity. Plus infinity. And since we are playing with the main player and it's not a terminal node, we will generate its successors. The first one is F, and we will give it a value of minus infinity. Since F is not a terminal state, we will generate its successors, which are L and M. For L, the utility value will be 12, and we will take the maximum between 12 and minus infinity, so it will be 12. And for the successor M, the utility value is 8, and we will take the maximum between 12 and 8, which is always 12. And we will back propagate the value of the node F, which is 12, between 12 and plus infinity. Here it's plus infinity, it's not minus infinity. We will take the minimum, which is 12. We will do the next expansion. So we will generate the node G. It's not a terminal node, and we are playing with the max player. So V is equal to minus infinity. We will generate the successors, which are the first one is N with a utility value of 9. We will choose the maximum between 9 and minus infinity. So it will be 9. Then we generate the next successor, which is D, and its utility value is 8, and take the maximum between 9 and 8, and it will be 9. We will back propagate the value of the node G, which is 9, and between the value of C, which is 12, and the value returned by the node G, which is 9, what is the minimum value? It is 9, so the new value for the node C will be 9, and we will back propagate this value to the parent node. In the parent node, what is the maximum between 12 and 9? It's 12, so we will keep the value of 12. And the action that will be chosen by the node, by the max player, will be what? Will be A1, because A1 is the action related to the value 12. Here I explained, but I didn't share. You didn't see the PowerPoint. I was explaining on the PowerPoint. I will send you the PowerPoint. I was explaining the PowerPoint, but I didn't share it. Oh, sorry. Is it clear? No, I was explain. I thought that I was sharing the whole. I was sharing only the one window. No, I was. I will show you. I was explaining on this. I was explaining on this. You understood the concept. Okay, I will send you the PowerPoint and you can see the change of the minimax value step by step. It's an animation, so you can use it to see the estimation of each node, of the minimax value of each node. But is it clear for the execution of the algorithm? Okay. It's simple. Now we will see another. Wait, I will change the. I will change. This is. It's better. So here. Yes. So here we will take another example on a game. So we will take the example of the tic-tac-toe game. So we will take as an initial game board this one. It's not the initial board in the game. So we will take just one in the middle of the game. And we will suppose we will keep the same setting as the first example. So the max player is the agent that we are creating the minimax algorithm for. He is playing with the cross and he is trying to win. So for the terminal state, the utility value is if it's a state which is a win for the max player, it will have a utility value of +1. If it's a loss for the max player, it will have a utility value of -1. And if a draw, it's 0. So we will see. This one. Now I think you are seeing the PowerPoint. So we will try to apply the minimax algorithm on this game. So the first step for the initial state. So is it a terminal state? No, we will give it a value. Since it's the max player, so we will give it a value of -infinity. Then we will do the expansion. We have 3 children. The first state or the first child, we are playing with the main player. So is it a terminal state? No. So we will give it a value of +infinity and do the expansion of the children. The first child, is at the 3rd level. So the first state, is it a terminal state? Yes. So here we can see that the first state has a line of knots, which is a winning state for the main player. So the utility value here will be equal to -1. So we will return this utility value to the parent node, -1. Between -1 and +infinity, what is the minimum value? It is -1, since we are playing with the main player. So the new value will be -1. Next, we will generate the second successor. So for the second successor, is it a terminal state? No. Since we are playing with the max player, so we will give it a value of -infinity and we will generate its successors. He has only one successor, so the last one. We can see that this terminal state is a winning state for the max player, so we will give it a utility value of +1. We will return this minimax value, which is what? between 1 and minus infinity, what is the maximum value? It is 1. So the new value of this state will be 1. Since we don't have other successors for this state, we will backpropagate its minimax value of 1. Between the current value of the state, the first state at the second level, which is minus 1, and the value returned by the second child, which is 1, what is the minimum value? It's minus 1. So we will keep the value minus 1 and backpropagate it to the root node. Between minus 1 and minus infinity, what is the maximum value? It's minus 1. We will generate the second successor. We will give it a value of plus infinity and generate its successors. The first successor is a terminal node and has a utility value of minus infinity since it's a winning state for the main player. So we will backpropagate this value. Between minus 1 and plus infinity, what is the minimum? It's minus 1. So the new value of this state will be minus 1. We will do the second expansion. Is it a terminal state? No. So we will give it a value of minus infinity and generate its successor. So it has only one successor, and it's a draw situation. So we will give it a utility value of 0 and then backpropagate this value. Between minus infinity and 0, what is the maximum? It's 0. And then backpropagate this value. Between minus 1 and 0, what is the minimum value? It's minus 1. And we will backpropagate this value since we don't have other successors. We will do between the value minus for the root node, between the value minus 1 and 0, what is the maximum? It's 0. So the new value is 0. We will do the last expansion. So the third child for the root node is not a terminal node. We will give it an initial value of minus infinity and do the expansion. For the first child, it's not a terminal node. We will give it a value of minus infinity and do the expansion. So it has only one child with a draw situation, so its utility value is 0. Between minus infinity and 0, what is the maximum? It's 0, and then we will backpropagate this value. Between 0 and minus infinity, what is the minimum? Oh, sorry, Lahna, I made a mistake. So here between 0 and minus infinity, we will keep minus infinity. I have made the mistake here. And then we will generate the second successor. For the second successor, we have, we'll give it the value minus, no, sorry, Lahnaya, it's plus infinity. It's not minus infinity. For the third child, it's plus infinity. I made a mistake at the second level. So it's plus infinity, and the new value will take the 0 value. So it's correct. We will expand the next successor, and we will give it a value of minus infinity. For this successor, it's not a terminal state. We will generate its successor, which has a utility value of plus 1 since it's a winning state for the max player. So we will backpropagate this value of 1. Between 1 and minus infinity, what is the maximum? It's 1. And when backpropagate this value of 1, between 1 and 0, what is the minimum? It's 0. And we will backpropagate the 0 value. Since here we already have a 0 value, so we will, between 0 and 0, we will keep the 0 of the second state. So here, for the max player, what is the best action? It will be the second one, because this action gives the highest minimax value. So it will choose to play with the second. It's the second or the third, but it will choose. The player will choose the first one. So it will choose the middle state. Is it clear till now? Okay. So now we will see some properties for the minimax algorithm. So here we can see that the minimax algorithm is what? It's just a depth first exploration. It's a DFS algorithm, but with two agents. So if we want to estimate the time and space complexity of the minimax algorithm, if the maximum depth is m, and B is the branching factor, which is equivalent to the number of legal moves for each player. So the time complexity will be what? Will be order of B to the power of M. Like DFS algorithm, it's order of B to the power of M. And if we want to estimate the space complexity, it's like in DFS, it's order of B times M. If we are generating all the successors at once, if we are generating one by one, which is the case in the recursive call, so the space complexity will be order of M. In the previous chapter, when we did the implementation of DFS, we didn't use a recursive function, but we can use a recursive function to implement the DFS. In the previous chapter, the idea was to use the same structure as the general search algorithm. That's why I didn't use a recursive function, but we can use a recursive function to implement the DFS algorithm. So here we can see that the time complexity is excessively high. So we will try, as we did for the DFS algorithm, we will try to limit the depth of the minimax algorithm. We will try to limit the game tree of the minimax algorithm. So here, what we will do, we will propose another version for the minimax algorithm, which is the depth limited minimax algorithm. So here we will do an expansion till we reach a depth limit and we stop the search. So obviously these nodes, when we stop the search, these nodes are not the game over nodes. They are not terminal nodes. They can be, but most of the time they are not game over nodes. So since we need the value of this node to estimate the minimax value of the root node, we have to find a technique or find a function to estimate the value of these terminal nodes, which are not game over nodes. For that, we will use a heuristic evaluation function. So instead of having a utility function, we will have a heuristic evaluation function. So here we will make some slight changes on the minimax value equation. So the first change will be what? We will replace the utility function by the heuristic evaluation function for the state S. And here the condition to stop the search, we will call it the cutoff test. The cutoff test will include the terminal test, and we test if we reach the depth limit or no. So the cutoff test is if S is a terminal state or we reach D is equal to 0. So D will start with the depth limit and we will decrement it till we reach the value of 0. This is the first change in the minimax value function. The second one, here we have like as a parameter, we will add another part in the previous minimax value. We have only the state and player. Here we will have the state, the depth, and the player. And here we will decrease or we will decrement the depth when we do the recursive call. These are the only differences between the minimax algorithm, the plain minimax algorithm, and the depth limited minimax algorithm. Now we will see the pseudocode. So here, for the first part, the minimax depth limited algorithm, we will have three parameters. We have the state, we have the depth limit, and we have the player. So the depth limit here can be 3 or 5, like as you want, which is the maximum depth of the game tree. Then here, for the minimax value, depth will change. So we'll start with the depth limit, and then we will decrease it until we reach the value of 0. Here it will be almost the same algorithm. For the first condition, in the plain minimax, the condition was if terminal state of a terminal test of state, we will return the utility value of the state. Here we have two conditions. The first one, if the state is a terminal state, or we reach the depth limit, which means the depth is equal to 0. We will do the cutoff. Here, we will not return the utility function, but we will return the heuristic evaluation function for the state. Then, for the remaining part of the algorithm, it will be almost the same. So we will check if the player is max, we will give it a value of plus infinity, then we will generate successors, then we will take the maximum between the current value and the minimax value of the successors. Here, we will just decrement the value of the depth. And it will be the same for the min player. So we will apply this depth limited minimax algorithm to the same example, which is the tic-tac-toe game. We will keep the same settings, which means that the max player is the AI agent. He is player with the cross, and it's the player which is trying to win the game. First, here we have to define the heuristic function. So the heuristic function, as like we see in the previous chapter for A star, it depends on the problem. So you have to define the heuristic function according to the problem. Here we can use this heuristic function. So since we have to keep in mind, so here the heuristic function has to follow the same concept as the utility function, which means that a higher value for the heuristic is favorable for the max player, and a low value for the heuristic is a bad, not favorable or a bad for the max player. So here the heuristic evaluation function, we will take difference between the number or total number of possible winning lines for the cross, since the max player is playing with the cross, minus the total number of possible winning lines for the opponent, which is the main player, which is playing with the nuts. So we can see here an example. So for this state, we can see that for the cross, for the player playing with the cross, it can form a line horizontally here, or here, or here. So we have 1, 2, 3, 4, 5, and 6. So here, x of s is equal to 6. So the cross can form 6 possible lines. We cannot form this line, since if we put another x here, we can never have a horizontal line here. For the nuts, we can see that we can form 5 possible winning paths. So we have this one, this one, this one, this one, and this one. So the heuristic value will be 6 minus 5, which is equal to 1. And we will do the same with apply the algorithm using this heuristic function. So here I used as an initial state this one, and the depth limit is 2 to avoid having like a huge game tree. So the first step, this state has 5 possible successors. So the max player here can put the cross in 5 possible squares, empty squares. For the first state, it's not a terminal state and we didn't reach the depth limit yet, so we'll do the expansion. For the third level of expansion, so we reach the depth limit, we will stop the search and we will consider these as terminal nodes, and we will estimate the heuristic value for each one of them. So for the first, we can see that we can the number of possible lines for the cross are 2. We have this one and we have this one. Here we cannot, if we put an X here, we cannot have a winner line. If we put it here, we cannot have a winner line since we have a knot here. So we have only 2 possible winning lines, which are this one and this one. So here we have 2, and the number of winning lines for the knots are this one and this one only. So we have only 1 possible winning line. So the heuristic value will be equal to 2 minus 1, which is 1. So the heuristic value for the first state is 1. So we will back propagate it to this node. Since here we have plus infinity and we will take the minimum, so the minimum will be 1. We will do the expansion for the next node. So here the number of possible winning lines for the cross is this one or this one or this one. So we have 3 possible lines. And for the knots, we have only this one. So we have 3 minus 1, which is 2. So the heuristic value for this state is 2. We will back propagate it. We will back propagate it to the parent node. Since we have a value of 1 and the returned value here is 2 and we are minimizing the value, so we keep the value of 1. We will do the same for the other states. So here between 1, 2, 1 and 2, so the minimum will be 1, so we will take the first state. So this one, we'll take the first action and we will back propagate the value 1 to the root node. Since here the value is minus infinity and we take the maximum, so the value will be 1. We will do the expansion for the second node. So the second node, this one, is not a terminal node and we didn't reach the depth limit yet. So we will do another expansion for the third level expansion. So we have the first state. Here we can see that this state is a winning state for the min player. So here we will not use minus 1 and plus 1 like in the utility function. If a state, so the heuristic value for a game over state, if it's a winning state for the max player, we will give it plus infinity, and if it's a lost state for the max player, we will give it a minus infinity. So here, since it's a winning state for the min player, we will give it a heuristic value of minus infinity. And we will estimate the heuristic values for the other states. So the other states are not game over states. So the first one, we have, for the cross, we have this line, and this line. So we have 3. And for the nodes, we have this one and this one. So we have 2 and difference is 1. So the heuristic value for this state is 1. And we will do the same for the other states. Since here we are playing with the min player, so it will take the minimum, which is minus infinity. It will back propagate it to the root node. Between minus infinity and 1, the max player will keep the value of 1. And we will do the same thing for the remaining successors, and we can see here that the first one is back propagating, is returning the value of 1, the second minus infinity, the third minus infinity, the fourth minus infinity, and the last one minus infinity. Since we are playing with the max player, which maximizes the value, it will take this one, the plus 1 value, and the chosen action will be this one. So the cross will be, the max player will put the cross in this case, in this square. So is it clear for the depth limited minimax algorithm? Okay. So next, we just saw the first improvement for the minimax, for the plain minimax algorithm. Now we will further improve the minimax algorithm by introducing what we call the alpha beta pruning technique. So even with the depth limited minimax algorithm, the algorithm is still not efficient, since we can, in order to have a very good estimation of the heuristic function, we have to choose like a high value for the depth limit. So in order to do a faster search and more in-depth search, we will adopt what we call alpha beta pruning technique. So first we will see, so the alpha beta pruning technique will do what? Will do a pruning of some branches in the game tree. If I say that, for instance, this branch is not useful for the search, this branch will not return a better value for the max player, I will not expand it, I will not explore it, I will cut it off, I will prune it. So what is the intuition behind the alpha beta pruning technique? So we can see this example. So for this example, we have a node A. And from the node A, we can do the expansion of three children nodes, B, C, and D. And the player is the min player. Here we can see for the node B, the minimax value will be 1, since here the heuristic or the utility will not, it's the same concept. So here the values returned by the children are 15, 6, and 1, and we will take the minimum value, which is 1. So the value of the node B is 1. We will backpropagate this value to the node A initially. Initially, the node A has a value of minus infinity. The maximum is 1, so the current value is 1. We will do the expansion of the second child. And for the second child, we can see that its successors have values of 3, 11, and 7. So we will take the minimum, which is 3, and backpropagate it. Since here we have v equal to 1, and we will take the maximum between 3 and 1. So the value, the current value of A will be 3. For the last child, which is the node D, when we do the expansion of its first successor, so the value returned by this successor is 2. So here, before doing the remaining expansions, we are sure that since the node D is a node played by the min player, so we are pretty sure that this node will choose a value which is less or equal than 2, since the first value, the value returned by the first successor is 2. So we call this value Z. So we are sure that Z is less or equal than 2. So whatever are the values of X and Y, if these values are greater than 2, the node D won't take them into consideration, because it will take the minimum. If they are less than 2, they will the node D will take them into consideration, but we are sure they are less or equal than 2. But here, the node D will return the value Z, which is less or equal than 2. Since the node A, which is played by the max player, has already a better value, which is the value 3. So we are sure that the node A will not take into consideration the value returned by the node D. It will always keep the value 3. So here, the idea behind the pruning, if for a successor node, if its first successor return a value which is less than the value, the maximum value in the parent node, it has no sense to do the expansion. Here, it has no sense to do the expansion of x and y, because we are sure that the value that will be chosen by the node D is less or equal than 2, and this value is not interesting for the max player, for the node A, because this node has already a better value. So this is the idea behind the alpha-beta pruning technique. So if we want to formulate this technique, so here we just saw the intuition. So if we want to see the equation, so here the minimax value of A will be what? Will be the max of mean 15, 6, and 1, the mean of 3, 11, and 7, and the mean of 2, x, and y. So it will be the maximum between 1, 3, and minimum 2x and y. So if we call this minimum 2x and y z, we are sure that z is less or equal than 2. So the maximum between 1, 3, and z, whatever is the value of z, because we know it's less or equal than 2, the maximum will be 3. So it has no sense to know the value of z. So if we want to formulate this problem, we will define two parameters, the parameter alpha and the parameter beta. So alpha will represent the best value or the highest value, since we are using alpha for the max player. So it will be the highest value for the max player. So alpha is the value that guarantee the best or the highest value at the current level for the max player. So alpha will be updated by the max player, and its initial value will be equal to the initial value of the max player, which is minus infinity. Beta will be the best or the lowest value for the mean player. So with beta, the mean player will guarantee that it has the best value at the current level, and the beta will be updated by the mean player, and initially beta has a value of plus infinity. So alpha and beta here represent what? Alpha will represent the lower bound for the possible values for the max player. So the max player will not consider a value which is less than this lower bound alpha. And for the mean player, it's the same. Beta is the upper bound for the possible values for the mean player. So the mean player will not allow or will not consider any value which is greater than the value of beta. So alpha and beta in the algorithm, we have to pass them through the recursive call. Later we will see how we can use them. Before, I will explain how we can use alpha and how we can do alpha pruning and how we can do beta pruning. So we take the same example. So here, initially the node A. So initially the node A has a value of minus infinity, and we say that alpha is the lower bound for the possible values for the max player. So initially it's minus infinity. So since until now the best value is minus infinity, we do the first expansion. The node B will return the value of 1. So the new value for the node A will be 1, since it's the maximum between minus infinity and 1, and we will update the value of alpha. So alpha is equal to the current value of the node A. We do the second expansion. The second expansion, the second node, which is C, will return a value of 3, and this value is greater than 1. So the new value of A is 3, and the new value of alpha is 3. So alpha here is the lower bound for the possible values of A, which means that if we find a value which is less than alpha, we will not consider it. So for the next expansion, we have the node D. For the node D, we do the first expansion. So the first expansion returns a value of 2. So here, after doing this expansion, if in the other branches or the other successors have values which are greater than 2, we will not consider them, since for the D node, we are playing with the min player. So here the value will be 2. And since we are sure that here, like the best value for the node D will be what? Will be 2. And this value is less than the lower bound of the range of the node A. So it's not interesting to look for the other values of the other branches, because we are sure that we will not find a value which is greater than the lower bound of the node A. So here, so this is the parent node, which is the max node. So after the second expansion, the lower bound for the max player is alpha, which is equal to 3. So the max player, or the parent node, which is A, will not take into consideration any value which is less than 3. So the range of values considered by max are from 3 to plus infinity. For the child node, from the first expansion, we can see that the value will never be greater than 2. So the range of values considered by the min player are from minus infinity to 2. So there is no intersection between the range of values considered by min and the range of values considered by max. Why? Because 2 is less or equal than alpha. So here the condition to do the pruning or to cut off the branches is to check if the current value is less or equal than alpha. And we will do the same thing for beta. So for beta, we will start with the main player. So initially, the value is plus infinity. We will update this value, since here the value returned by the B node is 10. So it will be 10. And beta, the upper bound for the node A is 10. Then we do the second expansion. The value is 8. We will return this value between 10 and 8. Since we are playing with the min player, we will take the minimum, so it will be 8. So the current value of A is 8. And also the upper bound for a beta, or the upper bound for the possible values for the node A, is 8. We do the next expansion. For the next expansion, the first node will return a value of 9. So the value of the D node is 9. Here we are sure that if the other successors have values less than 9, we will not take them into consideration in the node D. We will take the value 9. So here, the maximum value that we can, so here the minimum value that we can accept is 9. So if this node has values greater than 9, we will accept them. If they have values less than 9, we will refuse them. We will not take them into consideration. But here, since the minimum value that will be taken into consideration is 9. And here we already have a better value for the mean player, which is 8. And since the mean player, we want to minimize this value. So this 9 will never be taken into consideration. So here it's the same concept for the parent node. When we do the second expansion, the range of values considered by the player max is from minus infinity to the upper bound, which is beta, equal to 8. For the child node, from the first expansion, we know that the minimum value that will be returned by the node D will be equal to 9. So the range of values considered by the max player will be from 9 to plus infinity. And there is no intersection between the two ranges, since here the value, which is 9, is greater or equal than beta. So the first condition we will do the cutoff or the pruning is the value is less or equal than alpha. And here we will do the cutoff or the pruning if the value is greater or equal than beta. So now we will summarize this explanation in the algorithm. So we will add these conditions into the minimax algorithm. So the first part is always the same. So here we will apply the alpha beta pruning technique on the depth limited minimax. So the only difference, the values of alpha and beta, we have them as parameters for max value function. So initially, alpha has a value of minus infinity, and beta has a value of plus infinity. Then we will call the minimax value. First step, we check if we reach the depth limit of it or its terminal state. We will return the heuristic evaluation function for the state. Then we will check. Otherwise, we will check if the player is the max player. So we will give it a value of minus infinity. We will generate the successors for the current state. And for each successor, we will take the maximum between V and the minimax value of the successors with depth minus 1. Here, we always keep using alpha and beta with the mean player. Then we will check if the value returned by the successors, by the one of the successor, is greater or equal than beta. The condition that we just saw in the example is greater or equal than beta. We will do what? We will return this value, which means that we are applying beta cutoff. We are applying beta pruning. And we'll update the value of alpha, which is otherwise, we will do what? We will update the value of alpha, which is we will take the best value, which is the maximum between alpha and V, since we are playing with the max player. We'll do the same thing for the mean player. So initially, the value is plus infinity. We will generate the successors. We will take the minimum between the current value and the minimax value of the successor. If the value of the first or the second or any successor is less or equal than alpha, so we will apply a pruning. So we will return the value of V and do. So here, if we return, so we will stop here this loop. So we will stop the remaining expansions. So we will apply an alpha cutoff. Otherwise, if we will continue the expansion at this level, we will update the value of beta, which is the minimum between beta and V. So here we can see that alpha is updated by the max player and beta is updated by the mean player. Alpha is the best option or the best value reached until now for the max player, and beta is the best value reached until now for the mean player. So we will see this example and stop. So here is the example. So first step, we will call the minimax alpha beta pruning on the first node played by the max player. So it's not a terminal state, so we will give it a value of, I didn't update this. Manish. Yes, we will give it a value of minus infinity. So alpha initially is minus infinity and beta initially is plus infinity. Then we will do the expansion. So the first expansion, it's this node. It's the main player, so we will give it a value of plus infinity. For alpha and beta, we will just pass the values of the parent node to the child node. So we will keep the same values here. So alpha is minus infinity and beta is plus infinity. We will do the next expansion. And the node will have a value of minus infinity since it's the max player. Alpha is minus infinity and beta is minus infinity. Then we will do the next expansion. It's a terminal node. It will return the heuristic value, which is 5. Between 5 and minus infinity, what is the maximum value? It's 5. So we will update the maximum value. It become 5. Then we will check the condition. The condition for the max player is if the value is greater or equal than beta. So if 5 is greater or equal than plus infinity, no. So we will not stop at the expansion. We will not do a pruning. We will just update the value of alpha. So alpha is equal to the maximum of alpha and v. So initially alpha has a value of minus infinity. V has a value of 5. So the maximum is 5. So the new value of alpha is 5. We do the next expansion. The next node will return a value of 9. Between 9 and 5, what is the maximum? The maximum is 9. Is the value greater or equal than beta? No. So we will not prune any branch, and we will update the value of alpha with the maximum between 5 and 9, which is 9. We don't have another expansion, so we backpropagate the value of this node, which is 9. Between 9 and plus infinity, what is the minimum value? It is 9. So here we will check, is the value less or equal than alpha? Since we are using the mean player, no, so we will not do a pruning. We just update the value of beta, and it will be the minimum value between plus infinity and the current value, which is 9. So beta is equal to 9. Then we will do the expansion. Here, when we do the expansion, since we are passing the values of alpha and beta to the child node. So for this child node, v is equal to minus infinity, alpha is equal to minus infinity, and beta is equal to 9. We will do an expansion, and the first node will return, the first child will return the utility value of 10. Between 10 and minus infinity, what is the max? It's 10. So we will update the value to 10. We will check, is the value greater or equal than beta? Yes, 10 is greater or equal than beta. So we will return v. What does it mean? We will cut off this branch. So we will not explore this second successor, and we will return directly the value of this node, which is 10. Then between 10 and 9, what is the best value for the mean player? Obviously, it's 9. So we will keep the 9 value. Is 9 less or equal than alpha? No. So, and we don't have any other successor to cut off. So we will keep the same value. So value 9, alpha minus infinity, and beta, it's the best value, which is 9. And we do the back propagation of the value 9. Next step, we will update the values of the root node. So the value will be equal to 9, since the maximum between minus infinity and 9 is 9. Is the value greater or equal than beta? No. So we will not cut off this branch, and we will update the value of alpha, which is the maximum between the current alpha, which is minus infinity, and the current value, which is 9. And we will pass the values of alpha and beta to the next successor. For the next successor, the value, since it's the mean player, it's plus infinity, we will do another expansion. Same thing, it's not a terminal state, so we will do another expansion. So for the first terminal state, it will return the value of 3. We'll update between 3 and minus infinity. What is the maximum? It's 3. So the current value is 3. Is the current value greater or equal than beta? No. So we will not prune any branch. We will update for alpha, we'll take the maximum between the current value and the previous alpha, which is 9. So we will keep alpha equal to 9. And we do the next expansion that will return a value of minus 3. So between minus 3 and 3, what is the maximum? It's always value 3. And we will keep the same value for alpha and beta. And we will return the value 3. So between 3 and plus infinity, what is the minimum? The minimum is 3. Is the value less or equal than alpha? Yes, 3 is less or equal than 9. So we will cut off, or we will prune this branch, and we will return directly the value of this node, which is 3. And here, since we apply a pruning, we know that this tree will not be taken into consideration by the root node. So we will keep the same value for the max node. So obviously, the max player will choose the action related to the value of 9, which is the A1 function, the A1 action. So is it clear? Est-ce que c'est clair? C'est clair pour tout le monde? Ok. Donc, on va s'arrêter ici. Donc, on va s'arrêter là. TP de cette semaine, on va faire une application sur ça. Donc, on va créer donc le projet, le nouveau projet, ce sera juste la création de game tree minimax, alpha, beta pruning. Majoritairement, c'est ça. Qu'est-ce que j'allais dire? Donc, le mercredi, Inch'Allah, on va continuer le cours. La semaine prochaine, Inch'Allah, vous aurez une interrogation. Normalement, ici, parce que le chapitre il n'est pas très, très long. Donc, là, on va terminer le chapitre ce mercredi. La semaine prochaine, vous aurez une interrogation qui va porter sur les 2 chapitres. D'accord? Donc, vous informez vos camarades qui sont, la majorité sont absents. Donc, c'est tout. On se voit lundi, Inch'Allah. Bonne journée.